In this lecture, we'll discuss the shortest path algorithms or shortest path trees algorithms. So, what's the shortest path? Actually, our shortest path is that if we have a weighted graph, or if the weights of all the edges is same, we can still say that this is a weighted graph. We need to find the path between two given vertices that has the least cost. So that's the challenge here, because there would be many paths that lead us to destination from a given node. So we need to compare those paths and find the shortest path from them. Using a naive algorithm is actually too costly, so we would not find a naive algorithm. Instead, we have a few algorithms. So let's just see some applications, and then we'll go through the first algorithm, that is the Dijkstra algorithm, in this lecture. So length of a path in a weighted graph is actually the sum of all the weights. Okay, it's the sum of all the weights of the edges that are used in this specific path. Okay, so for example, from vertex number 1 to vertex number 13, this vertex, these two vertices. So if this is the source vertex, this is the source vertex, and this is the destination vertex. So we need to find the shortest path. We have many choices here. We could have taken this path, taking this edge 5, then this edge 1, 2, 6, 3. So that has cost 5 plus 1 plus 2 plus 6 plus 3. So that's the cost of using this path to reach node number 13. Similarly, we can have 5 plus 3 plus 2 plus 1 plus 3. So there are many options. Which one is the best option here? Okay, so perhaps this is the best option. 5 plus 3, 8, 8 plus 2, 10, 10 plus 1, 11 plus 3, 14. So there's the cost of this path is 14. Okay, so perhaps this is the minimum cost or the shortest path for this specific from this source to this destination node. Okay, so the applications are that if we want to design a circuit, what we want to know is that we want to reduce the time for a change in input to affect the output. Okay, so we would need to keep the shortest path in the circuit. So we actually encounter the minimum delays. Okay, then an application that is regarding the computer networks. In computer networks, if we talk about the internet is actually a collection of different interconnected computers. So we have all the computers in the world, and then they are connected via maybe fiber optic or different wires, and they make a network, and the network of all those networks is the internet. Okay, what happens is that the information passes through that network, and from a source it reaches a destination. Okay, so there are different routers and different machines in between these two these two actually endpoints between source and vertex. So we can represent this overall information using a graph. We can have different vertices as to represent different routers, and then there are lines that show the connectivity of these routers with different other routers. So this makes, maybe there are different duplicacy of paths as well. So we have this kind of a formation that we can actually represent it as a graph. So okay, now we have represented a computer network using a graph. So the application of a graph is that if we want to send a packet through such a dense network, that and we have shown the graph of this network. If we want to pass the information maybe from this specific node to this specific node, we have to find a shortest path from this very dense graph. So this means that this challenge is actually very important, because the choices we have are so many that we actually want to come up with an algorithm that is efficient enough to give us a result in a reasonable amount of time. Okay, and we can save those results for some time, and then we can again run the same algorithm to update the weights, because these networks, computer networks, they actually change very quickly. maybe a node goes down, maybe a computer shuts down, or maybe a router malfunctions somewhere between. So we need to keep updating these actually shortest path information as well. Okay, so that's another application. The matrices to measure the shortest path for a computer network can be the low latency. That is, the path that actually has more bandwidth. Maybe it gives me the lowest time from source to destination. Maybe there is another way in which I'm interested in just counting the number of vertices that come in between the two different computers. Maybe it's important because sometimes, maybe for security reasons, I do not want my packet to pass through many entities in the graph. So I just want it to pass through as few number of computers as possible. So that's another metric of finding the shortest path. So there can be many different matrices as well. So whatever the metric we use to find the minimum or the shortest path, that would be counted. That metric would be counted as the cost of the edge in the graph. Okay, okay. Then there is this, of course, very common application where we have this map, and what we do is that we find a shortest distance from, or a shortest path on which I can travel from one source to a destination. So that's very popular application of shortest paths as well. So I hope it's very clear that a shortest path, finding shortest paths among different entities in a graph is very important. Okay, so let's just say that given a graph G that has a set of vertices and a set of edges, we have different variants as well, because we need to find shortest path in different ways. The first way is we want to um, find shortest path from one node, from one position to all other positions. So that's single source shortest path. So we have one single specific location, and we want to explore the entire graph to find the distances from this vertex to all other vertices. So that's single source. Then there's single destination. That's the opposite of single source. That for this given vertex, we want to see the cost of all the vertices to reach this vertex. Maybe for some specific event, we would like to see how many different paths we can have to reach a specific venue. Okay, and for single source, what we can have is that maybe when the event is finished, we would like people to go back to their homes, and we would like to find the distances from this specific venue to all the places or all the residences of the people that have come to this specific event. So these are two opposite types of problems. Then we have this single pair shortest path, that we have one source and a destination, and there is an entire graph in between. That's an entire forest maybe. So from this source, we need to reach this destination, and we have multiple options. We want to pick the best one. So that's single pair. We want to maybe pick this path that is the shortest to reach this destination from the source node. So this is called a single pair shortest path. We have different algorithms for all these types of uh, problems. And the last problem is all pairs shortest path. So in this specific case, as I said earlier, that in a computer network, we would need to update the entire graph or the information of the shortest paths for the entire graph at one point, and then we update it at a later stage as well. So for that specific case, we need to update all pairs, that is from every node to every other node. So for example, if this is v1, this is v2, and this is v3, for this all pair shortest paths, we would update the cost between v1 and v3, v1 and v2, and v2 and v3. So all pairs shortest path is another type of problem that shortest path algorithms, uh, for which shortest path of algorithms are developed. Okay, so there are four types of algorithms, but we would actually go with this one where we have single source shortest path. We'll start from one specific vertex, and we would find the shortest path to all other vertices, and that is the single source shortest path, and the algorithm is Dijkstra's algorithm. Dijkstra is the name of the mathematician who invented this specific algorithm. So the algorithm is very simple and similar to the Prim's algorithm. We'll see how. So the idea is that we would maintain a set, that is the set S of the vertices uh, that are actually explored, and we know the distance to these vertices from the starting vertex. Okay, initially that would be empty, and then we would actually populate this set by a depth first search algorithm that is again very similar to the Prim's algorithm that we discussed in the previous lecture of minimum spanning trees. So we would follow the same idea of moving from one vertex to the other vertex, but this time we would actually keep the cost of the entire path from the source to this current vertex. Okay, so we would keep updating the distances whenever we find a vertex that has a bigger distance already discovered and we have found a new distance that is smaller. So we would update that vertex with the new information, and that would actually eventually give us a shortest path to this current vertex. So let's see the algorithm. The algorithm is it actually looks very similar to the Prim's algorithm as well. So the idea is initially the distances are distance from the source node is 0 because it's the starting node. Parent of this node is null because this is actually the if we would maintain the priority queue here. So in the priority queue, this starting node should be the root. So it has no parent. Then what we would do is that for all the vertices, okay, initially this set is empty. So what we have is that we would actually pick all the vertices and update their distance to be infinity because we do not know the distance of any vertex from the source vertex. Then we set this as infinite as an empty set, and after that we would add all the vertices into the minimum priority queue. All the vertices have caused this infinity, so the all the vertices would go at the lower levels of the minimum priority queue, and this node, starting node, this source node would be the root node. Okay, after doing this, what we would do is that we would run through this loop. This is a while loop, in which we'll just keep checking the queue. We will pick the minimum value in the queue that is on the top, and then we would add that specific vertex into the set that this vertex is now processed. Okay, once this vertex is out of the queue, we say that the vertex is processed, and the processing is this for loop. What we do here is that we pick all the adjacent vertices of this vertex u, all the neighbors of u, and we check the distance to reach this new vertex. This is the distance that we know so far. Initially, the distance of all the vertices was infinity. Remember, this was infinity. So we do not know the cost of the vertices at beforehand, but when we start processing, the cost keeps updating. So we would compare this current cost of the vertex v, that is neighbor of u, with the cost that can be the new cost of this vertex, and this actually presents the cost of the edge between u and v node. U is the node that we are processing. So if, for example, this is a u node and it has two nodes connected, we call them v1 and v2. So what we are doing here is that this cost of this edge is actually weight between u and v1, and this is weight between u and v2. Okay, so we would compare the cost of u. Maybe the cost of u is, maybe I say cu. So we say that in order to reach this node u, I have encountered this, no, this value, this cost cu. So I add this cost of the uv1 in this cu and say if this cost is smaller than the initial, the already known cost of v1. If this new cost is smaller, then I update this cost, this weight of vertex v, and then I set the parent of v as this node u. So this u would become the parent of v1. Similarly, we would update the cost of the second vertex as well. So that's the entire algorithm. It's very similar to Prim's algorithm. In fact, if you see them side by side, the only difference between these two algorithms is these red lines. So in the if, what we do is that in Prim's algorithm, we just compare the cost of current vertex, current edge with the previous key. Whereas for the path, we do not consider only the edge, we consider the cost of this edge and the distance to reach the node u. Okay, the cost that we have encountered to reach this node u, we add this cost in the cost of the edge, and then we compare the new weight with the current key or the current distance of the node v. So that's the distance where we accumulate the entire cost of the path in Dijkstra algorithm, and in the Prim's algorithm we just note the cost of the current edge. Okay, that's one difference. And then the second difference is, of course, that if this compared cost, whatever we have compared with the current cost, if the new cost is smaller, then we update this new cost and we save this new cost in the distance of the current vertex. So that's the only difference between between the Prim's algorithm and the Dijkstra's algorithm. So let's run an example. So if we have this graph, we have five different vertices and several different edges. So for this specific algorithm, what we do is that we maintain a queue here. That's the minimum priority queue, and the initialization is already done here. And that was the first few lines of the code, that we have set the cost of all the other vertices as infinity and the cost of the starting node. This node A is the starting node. We set the cost as 0 because this is the starting node. The cost from A to A is 0. Then this is the set which we would keep updating, and we would put all the processed vertices in this edge. And this is the table that actually have different variables. So distance of a vertex from node A and the parent of that specific vertex. So for this vertex A, the distance is 0 and the parent is no one because this is the first or the root of the priority queue. So we would start by extracting the minimum node from this queue. So minimum value is this one or this one. So we extract this specific vertex and now put this vertex in the set of processed nodes. Now from this vertex, we update the cost of the adjacent nodes after comparing the current cost with the new cost. So the cost of this node A is 0, and the cost to reach this node C would be 0 plus 3, that is 3. So initial cost of C is infinity, the known cost of C is infinity. We are comparing this cost with the value 3. And for this node B, the initial cost is infinity, and we are comparing this with 0 plus 10. 0 plus 10, that is 10. So both the new values are smaller than infinity, so we would update the costs of B and C. Okay, this A node is now processed. From the remaining vertices, we have this C that has the minimum cost. So we would remove this. This C is now the root of the minimum heap. So we would remove this C from the queue, and for this C, the adjacent vertices are this B again, this D, and this E. All these three vertices are adjacent to C. Remember, the edges here are directed edges. So the cost of C is 3. So for this edge, the cost would be 3 plus 4, 7. We would check if 7 is less than the already known cost of B, that is 10. Of course, 7 is smaller than 10, so we would update this cost of B. Then we would compare this 3 plus 8. 3 plus 8 with the cost of D, that is infinity. So 11 is less than infinity, so we would update 11 here. And for E, 3 plus 2, 3 is the cost of node C. So 3 plus 2, 5 is less than infinity, so we would update E as 5. Okay, so now this C is also processed. We have put this C in the set of processed nodes. Now, from the remaining nodes, this 5 is the smallest cost. So this is the root of the minimum heap. So we would remove this E from the queue and put this in the set. And from E, the only neighbor is this D. So the cost of E was 5. So 5 plus 9, 9 plus 5, this is 14. The initial cost of D is 11. We are comparing this 11 with 14, so we would not update 14. 11 is already the shorter or the maybe shortest cost here. Shorter cost here. So we would not update anything via E. So now from the remaining two vertices from D and B, the smaller cost is of B. So we would remove this B from the vertex from the set. Okay, so removing B from the set, the cost of B is 7, and the adjacent nodes are 7 plus 1 8 C, but C is already in this set. So we would not process the nodes that are already processed. Okay, so we would not check the cost of C. We would only check the cost of this edge. So the cost of B is 7. 7 plus 2. The cost becomes 9. So we are comparing this 9 with the value 11 for node D. So this 9 is definitely a shorter path. So we would update this 11 with the value 9. So now the last node in the queue is D. We just extract that node, and all the neighboring nodes are already processed. So we would not do anything for this node D. Okay, so after this, the queue is empty. We have already extracted all the vertices from the queue, so queue is empty, and the while loop of the algorithm terminates, and the algorithm terminates. So if we see here in the parents list, what we have is that, for example, um, that's very important to discuss here, that if, for example, I want to visit the node E, so what is the path to reach the destination E from the node A? So I would see the parent of E, which means that in order to reach this node E, I need to visit C first, which means that I need to take this edge. Okay, so I reach C. So how do I reach C from the node A? So I check the parent of node C, that is A, which means that I would simply use this direct connection between C and A. So in order to reach A, the path that I have found is that from A I would reach C, and from C I would reach E. It would be interesting to write an algorithm or a code to actually display this path in the correct sequence. That is, first it displays that I would take the edge that costs 3, and I would move from A to C. Then from C, I would take the edge that costs 2, and I would move from C to E. And that is what I want to display when I display the path of node E. In this specific array, I have the path in the reverse sequence. So I hope you already got the idea that in order to print the sequence in the correct order, that the order is A, C, and then E, I would need something that reverses the current sequence. So for that, definitely we use a stack. So from E, we put E in the stack, then we put the parent of E in the stack, then we put the parent of C in the stack, and then we reach the destination. So the stack now has all the nodes that are in the path, and if I now pick the or pop the top value, that would be A, then pop the second value, it would be C, then pop the third value, it would be E, and now I have the correct sequence. So writing this code is an interesting thing. I think this should be you should actually practice this, and you should come up with the code in the next lecture as well. So that was the last step or the last information that we should know before moving on. You can also try this graph to practice. I would not actually go through the details of this graph in this lecture, but we have the slides ready for this graph. I would share those slides with you. You can actually go through this graph on your own and then see your solution and compare your solution with the solution given in the slides. Um, Whereas what I want to discuss here is that the some comments on the Dijkstra algorithm, that if I want to find in fact, if I just see that the cost of all the remaining vertices in the priority queue is infinity, what does this represent? that I have processed some part of the graph, and I have maybe two or three vertices that are left in the queue, but the cost of all these vertices is still infinity. There is no node in the queue who has cost less than infinity. So this means that this portion of the graph is not visited, and I have visited all the remaining vertices, which means this portion is disconnected from the graph. Okay, so again, is just like the Prim's algorithm, this Dijkstra algorithm also does not work on the disconnected graphs. Then, if I want to find the distance between two vertices, that is the what we can say is the a pair distance between a pair of the vertices. So I would just run the Dijkstra algorithm instead of running any different algorithm. We can just use the Dijkstra algorithm and stop where we remove this destination vertex from the queue. Okay, so we can stop our Dijkstra algorithm on that specific vertex, that is the destination vertex, and that would be the solution to find the shortest path from nodes j to k. Okay, and then uh, this algorithm also works for the directed graphs. Okay, so directed or undirected graph, it doesn't make any difference to the Dijkstra algorithm. It just sees if it can take a path from one node to another or not. So having a directed graph doesn't make any difference to this algorithm. So that's the last point that I want to discuss here, is that this Dijkstra algorithm, it does not work when there is a negative edge, and the cost of edge is so big that if I have a cycle in the graph, the cost of the cycle becomes negative. Okay, so if I see these three vertices C, D, and F, the cost between these vertices is the cost of these edges 1 plus 5 minus 8, that is minus 2. So the cost of this cycle is minus 2. So if I keep repeating in this cycle, the cost would keep decreasing, minus 2, minus 2, minus 2. It means that the Dijkstra algorithm, if there is a negative cycle in the graph, it actually goes into an infinite loop, because it's a greedy algorithm, and it would always try to reduce the cost of one node. So what we would do is that uh, we would actually get stuck in this loop. Okay, so we cannot run a the Dijkstra algorithm to find the shortest path if there are negative edges in the graph. So that's it for the shortest path algorithms. We have a few more algorithms for to find the shortest path, but for this course, the Dijkstra algorithm is actually included, and the other algorithms that are the flight algorithm, that is not included in the course. So that's it for the shortest path algorithm.